Hello, this is Ms. DB, and in this lesson we're going to learn about Chapter 6, Section 1 on properties and attributes of polygons. Our objectives are to classify polygons based on their sides and angles, and also define and use measures of interior and exterior angles of polygons. After this section, we're going to concentrate on quadrilaterals. Alright, we have some various vocabulary here. Sides of a polygon, vertex, diagonal, a regular polygon, concave, and convex. So way back in Chapter 2, we learned about the definition of polygon, and now we're going to learn about the parts of a polygon and how to classify them. Alright, there is a investigation that goes along with the first section. That is your journal for week 15. So you want to do that journal now, probably before you do the first assignment. And when you do it, you're going to be drawing the diagonals of various polygons. And when you make a diagonal, you start at one vertex, you pick one, and then you draw all of the lines from that vertex to the other vertices. So when I draw, if I pick B to be my common vertex here, then I can't really draw a diagonal from B to C because I would just retrace the side of the polygon. So I draw one from B to D, and I could draw one from B to E, and I can't really draw one from B to A. So this polygon has 2 diagonals, and it created 1, 2, 3 triangles when I did that. Anyway, so we have that there's a side of a polygon, and the common endpoint of 2 sides is the vertex, and a segment that connects any 2 non-consecutive vertices is a diagonal. We name a polygon by the number of sides. There's special names all the way up to, I don't know, like 24 or something, but here's the ones that you need to know. So 3 is a triangle, you know that one. 4 is a quadrilateral. 5 is a pentagon. 6 sides is a hexagon. 7 sides is a heptagon. 8 sides is an octagon. 9 sides is a nonagon. 10 sides is a decagon. 12 sides is a dodecagon. I don't even remember what 11 is. Don't worry about it. And anything else we'll just call an n-gon. Now remember, to be a polygon, you have to have only straight sides, and they have to connect. You can't have any gaps, like that wouldn't be a polygon. It has to be closed, in other words. This can't be. You can't have it hanging off the end like that. You can't have any curved pieces. They have to only be straight sides. So it has to be a closed figure made up of straight sides. Oh, here's the definition here. A closed plane figure formed by 3 or more segments that intersect only at their endpoints. So is this a polygon? If it's a polygon, name it by the number of sides. Well, it is a closed plane figure formed by 3 or more segments that intersect only at their endpoints. So yes, it is a polygon. And then we just count the number of sides. 1, 2, 3, 4, 5, 6. 6 sides is a, and this is in your book so you can look it up, hexagon, if you don't have it memorized yet. So it is a polygon, and it is a hexagon. Now this is a polygon. It looks a little different, but it is, and it's got 1, 2, 3, 4, 5, 6, 7 sides. So you might have to look it up, but that's called a heptagon, H-E-P-T. This is not a polygon because it is made up of curves. Doesn't fit the definition of polygon, so we can't name it by its number of sides. This is not a polygon because it's not closed. So it doesn't matter how many sides it has, it's not a polygon. You don't even have to count them. Alright, if you have all sides congruent, then you have an equilateral polygon. If all the angles are congruent, then it's equiangular. A regular polygon is one that is both equilateral and equiangular. In other words, a regular polygon has all congruent angles and all congruent sides. If it's not regular, it's irregular, IR, and then the regular. It's concave if any part of a diagonal contains points in the exterior of the polygon. If no diagonal contains points in the exterior, then the polygon is convex. A regular polygon is always convex. Here's some examples. A concave quadrilateral, I could connect this vertice to this vertice, and it would go outside of the figure. It would be an exterior line. So that makes it be concave. See, it kind of caves in. A convex quadrilateral, any diagonals that I draw will remain inside the interior of the polygon. That's called convex. So in this one, you're supposed to say whether it's regular, irregular, and concave or convex. Now, to be regular, it has to have all sides congruent. We've got that. And all angles congruent. We don't have that. So it's irregular. And then if I draw the diagonals, it's going to remain inside in the interior. So it is convex. Doesn't cave in anywhere. Okay, here we've got all right angles. Well, many right angles, not all right angles, because we've got this kind of thing going on here. It's irregular. We don't have congruent sides anyway, even though we have a lot of right angles. And it's concave because if I connected these 2 points here, these 2 vertices, I would have a diagonal going outside in the exterior of the polygon. Now here we have all sides congruent and all angles congruent. This is a regular. Finally, we get a regular polygon, and it's also convex. Remember that if it's regular, it's going to be convex. To find the sum of the interior angle measures of a convex polygon, draw all possible diagonals from one vertex of the polygon. This creates a set of triangles. This is your investigation for the journal for this week. The sum of the angle measures of all triangles equals the sum of the angle measures of the polygon. So here's an example of drawing the diagonals of a triangle. You really can't do it, so it's just 180 degrees. And of a quadrilateral, you can connect those 2 vertices to create 1, 2 triangles. And of a pentagon, we did that one earlier, you'd get 3 triangles, and of a hexagon, you'd get 1, 2, 3, 4. Now there's a relationship between the interior angles and how many triangles you can create. Since every triangle has 180 degrees in it, you can use that to help you find the measures, the sum of the measures of the interior angles of any polygon, no matter how many sides it has. So for your journal, you're going to take these different shapes, and some of them we just looked at, and there's some sketches, and you're going to sketch the diagonals of it. So here is a, let's see, how many sides is that? 1, 2, 3, 4, 5, 6-sided figure, which is a hexagon. So you're going to make all of the diagonals going from one vertice only. Remember, one vertex only. And it's got 6, which I was doing this one, 6 sides. I can make that into 4 triangles. So that means that I will take 4 times 180 to get the sum of measures of the interior angles. Because there will be 180 degrees in this one, 180 degrees in this one, and so on. So 180 degrees times 4 is how you'll find the sum of the interior angle measures. All right, in each convex polygon, the number of triangles formed is 2 less than the number of sides, n. This is kind of giving you the answer for the investigation. So there's this polygon angle sum theorem, which you will develop in your journal. All right, let's use that. It says find the sum of the interior angle measures of a convex heptagon. So you might have to look it up on your table, but a heptagon has 7 sides. So we'll use the formula that says that means there'll be 5 triangles formed if I drew all the diagonals. So 7 minus 2 is 5. And then take 5 times 180, and you will get your sum. Remember, this is the sum of all the interior angles in a heptagon. It'll be 900 degrees. This one doesn't have a special name. It just says 16gon. And it says find the measure of each interior angle of a regular. That's different. The last one said find the sum of all of the interior angle measures of just any old heptagon. This is different because they're asking you to find each interior angle of a regular 16gon. I'm not going to be able to draw a 16gon very well, but it's going to be 1, 2, 3, 4. This is going to be like an octagon. But pretend like you have a 16gon over here and that every one of these angles is the same. So if I could find the sum of all of them, whatever that sum is, and divide it by 16, because in a regular one, every one of these angles is the same. So that's what I need to do. I need to find the sum, which I would do by taking 16 minus 2, and then multiplying that by 180. So 14 times 180 is equal to 2,520. And then I still need to divide that by 16 because there's 16 of those angles that made up the 2,520. Because it's a regular. If we didn't know it was a regular, we wouldn't be able to do this. So 157.5 degrees is what each angle measure would be. Now in this one, it's not regular, it's just a pentagon, but they're giving us expressions for these. So I could find the sum, because I know it's a pentagon, so I can take 5 minus 2 times 180, so 3 times 180 is 540, and then I just need to add up each of these, either what they tell me the angles are equal to sometimes, or the expressions for them, and that will all be equal to 540. So I replace measure of angle A with 35C, and measure of angle B with 18C, and so on. And then I combine my like terms to get 135C equals 540. Divide both sides, we're just solving for C now, to get that C is equal to 4. And then I would substitute in 4 in each of these expressions. Now, a couple of them are the same, so that's kind of nice. And when you do that, you'll find that measure of angle A is 140. Where's this one? 140, because 4 times 35. And 18 times 4 is, let's see, 72. So this would be 72, and there's another 18C. This would be 72. And 32 times 4 would be 128. That's what C and D would be. So you just use the same, what you got for the variable, and plug it in for each one of those. All right, now let's look at exterior angles. In the polygons below, an exterior angle has been measured at each vertex. Notice that in each case, the sum of the exterior angle measures is 360. Now you could develop this, but in this case, we're just letting you know that this plus this angle plus this angle, all of these exterior angles will add up to 360. And it doesn't matter whether it's a 3-sided polygon or a 5-sided polygon or a 100-sided polygon. The exterior angles always add up to 360. And you can kind of see that that's going to be true because you know there's 360 degrees in a triangle, in a circle. And the more sides you get on your polygon, the closer it looks to a circle. So eventually, you would be able to add them all up to get to 360 degrees. An exterior angle is formed by one side of a polygon and the extension of a consecutive side. That's the definition of exterior angle. So the theorem just says that the sum of the exterior angle measures of a convex polygon is 360 degrees. All right, so if we have a regular 20gon, they want us to find each exterior angle. Let's start with a regular, something easier. Pretend that this is regular anyway. This would be a 1, 2, 3, 4, 5, 6, 7, regular octagon. So if I know that the exterior angles will add up to 360, here, let me sketch those. This angle here, and this angle here, and this angle here, and this angle here, and this angle here. All 8 of those exterior angles will add up to 360. There's 8 of them. I'll just call it N. They're all the same. But this is a 20gon, not an 8gon. So in a octagon, you would just take this, divide by 8, and you'd get your answer. In a 20gon, you do the same thing, except it has 20 sides. So the measure of one exterior angle will be equal to 360 divided by 20, which is 18 degrees. Now this one's not regular, but we do know that if I were to add up all of these exterior angle measures, these expressions, they will equal 360. So we write an equation that says that. We add all of them up to equal 360. Then we combine any like terms that we have. In this case, there's a lot of them. And we divide. And we get the b is 3. Now, that's how they ask you to do in this one. Sometimes they'll say find the exterior angles, and then you would have to plug 3 back into each of these and find each angle. And it looks like they're all going to be different in this case. But that's all they ask for, so don't do more work than you have to, is to answer the b would be 3. Now, dodecagon, you might have to look this up on your table in your text, but that's a 12-sided figure. It's a regular. That means that we can find the measure of each. So you would take 12n equals 360, or just 360 divided by 12 to get that each of those would be 30 degrees. If they ever ask you for the sum of the exterior angles of a polygon, remember, it's always going to be 360. That would be like a trick question. You wouldn't have to do any work for that. You would just say, oh yeah, that's 360. It's a theorem. In this one, they ask us to find the value of r. That's not a big deal because we'll add all 4 of those exterior angles up, and that will be equal to 360. So we'd get 24r equals 360 divided by 24 to get r is equal to 15. And again, in this one, they didn't say find the measures of them. They could have. They could have even said find this angle. And if I know, let's see, r they said is 15. So if I take 8 times 15, 5 times 8 is 40, 8, 9, 10, 11. So it's 120 degrees right here, which means that x would be 60 because together these two are supplementary. They form a straight line. They're a linear pair. So you might have a problem where they ask you to go one more step and find the angle, an interior angle like that. And you could do that then. So good luck. Let me know if you have any questions and concerns, and I'll be happy to help you out. Thank you very much.